Hello everyone. So this module is about turbulence. So what all things I am going to teach in turbulence, if you see this slide. So the objectives of this module are definition of turbulence, decomposition of mean flow and fluctuating components, expressions for mean component and fluctuating component, and let's do the Reynolds averaging of differential equation of conservation of mass, differential equation of conservation of momentum, differential equation of conservation of energy. After we do this, we are going to get turbulent stress terms, so we will understand the physical significance of these turbulent stresses. So from there we shall introduce ourselves with the universal velocity profile, and then we shall understand closure problem and write these Reynolds averaged equations as boundary layer equations and introduce the concept of eddy momentum diffusivity and eddy thermal diffusivity. So from there we shall derive universal velocity profile, which we have introduced earlier and which will involve Prandtl's mixing length hypothesis. This is the plan for the next 2 to 3 modules. So let's get started with Reynolds experiment. See, whenever we do this, I think we have all done this experiment, Reynolds experiment. So in the Reynolds experiment, there is a pipe and I inject a dye, and this is, if it is laminar flow, the dye moves like a laminae. But that happens for Reynolds number less than 2100. Now, for transitional flow, that is for Reynolds numbers between 2100 to 4000, sometimes the flow is laminar, sometimes the flow is turbulent. So that is, it is transiting between laminar and turbulent. So that's why it is called transitional flow. Now for Reynolds number greater than 4000, the flow is turbulent. The dye is going to dance all the time, so the flow is going to be turbulent. So if you were to plot velocity versus time, this is steady in laminar flow. Transitional, as you can see, it is steady for some time and wavery for some other time. That's why it is transitional. For turbulent, it's going all the way, all the time it is wavering. So it's a wavy, it's turbulent flow. So can I get laminar flow for Reynolds numbers? Laminar flow. Can I get laminar flow for Reynolds numbers greater than 2100? Yes, we can get. But then what is this 2100? So far, to the best of my knowledge, as given in Schlichting, we have been able to get laminar flow for Reynolds number up to 40,000. But how? If you keep no disturbances upstream to the laminar. But then what is this 2100? No matter what disturbance you keep upstream, the flow is going to remain laminar for Reynolds number less than 2100. That is the significance of Reynolds number 2100. That means for Reynolds number 2100, you put a bend upstream, valve upstream, 90 degree bend or 180 degree bend or 180 degree out of plane bend. No matter what bend you put or what disturbance you create upstream, for Reynolds numbers less than 2100, flow is going to be inherently laminar. That is the speciality of this critical Reynolds number 2100. Now let us see the next, just a small test facility. This is a tank, and from this tank there is a flow taking place in this pipe, and there is a small bluff body in this pipe. That is, there is a cylinder inserted in this pipe, and this flow is again recirculated back to this tank. Now let us see this video. This bluff body, it is a cylinder, and this is a pipe. Now you see there are vortices being shed. The main flow is laminar, but the flow downstream the bluff body is turbulent. How do I know that it is turbulent? Because eddies are formed, vortices are shed. The very fact that there is a presence of vortex itself means that the flow is turbulent. Now let us take up a Reynolds number of 10,000. This is trapezoid. Okay, so you can see that the eddies are formed and they are shed at a faster rate than what you were seeing for laminar flow. So this is also a pipe, this is a trapezoid, and the flow is getting separated at this tip, and the pipe Reynolds number is 10,000. So with this background, let's get back to our fundamentals of Reynolds number. So is turbulent flow desirable all the time? Desirable situations of turbulent flow, because naturally the flows are turbulent, but they are helpful also. See, if you were to design a boiler or air conditioning cooling coil, the size of the boiler or the size of the air conditioner or the typical heat exchanger would be very large. Heat exchanger would be very, very large if the flow were to be laminar. If the flow is turbulent, if the flow is maintained turbulent, the heat exchanger size would come down. So that is one advantage you can see. And mixing of fluids. If let's say smoke is coming out of chimney, if the flow were to be turbulent, it would have taken enormous lengths before the smoke which is coming out will get diffused into the air. But because the smoke which is coming out of the chimney is inherently turbulent, it diffuses for a shorter length and faster. And then if you are mixing paints, same thing is for mixing paints also. So for mixing paints, so if it is turbulent, you can mix the paints very faster and very easily compared to mixing if it is laminar. Now, but then is laminar flow desirable? Is laminar flow desirable? Yes, there are few situations where flow is inherently laminar. You cannot make it turbulent. For example, you are pumping highly viscous oil. If you are pumping highly viscous oil, you will have to be maintaining, it will be inherently laminar, otherwise the pumping power would go up very large. Or blood flow in our arteries. Most of the arteries and veins, the blood flow is Reynolds number is less than 2000. So it is laminar. Why? Because the load on the heart would be less because the flow is laminar. So like that, there are very many situations where you would like to have turbulent and where flow you would like to have laminar. But inherently nature poses, most of the time nature poses turbulent flow. Nature poses turbulent flow. Okay. Now Reynolds and Taylor and Van Karman, they all attempted, how do one define turbulence? That is, definition of turbulence. Although it is a sentence, I would like to write this sentence. Turbulence is an irregular motion in which appears in fluids generally, that is gaseous or liquid. When does it occur? When flow past a solid, that is flow over a bluff body, solid surfaces, or neighboring streams flow past one another. That is, let us say one jet passing over another jet, passed over one another. That is smoke coming out of the chimney. So this was the first definition given by Taylor and Van Karman in 1937. But this definition didn't yield any which way to reduce this to mathematics, because the word irregular means highly chaotic. So how do you handle chaos? It becomes very difficult. So they modified this definition and came up with the following way. The turbulent fluid motion is an irregular motion. Yes, it is irregular motion, irregular condition of flow or irregular motion or condition of flow in which various quantities means it can be velocity, it can be pressure, it can be density, velocities and let us say pressure, show a random variation with time and space. So that this definition helps us so that statistically distinct average values can be discerned. So the first definition was highly chaotic, but the second definition, the word random, the usage of random has helped us to use statistics to define average values. So now with this, let us see how do we use statistics and define. So what do they do is, in turbulent flow, turbulent motion is decomposed into mean motion and fluctuating motion. So let us just say this is my velocity versus time. Okay. So let us say, how do we get, let us take this little later on. Now let us say this is my typical plot. If I have an imaginary probe which gives me the velocity as a function of time, this is what it is. So now this dashed line is the average component, u bar, that is turbulent motion is decomposed into two portions, that is mean motion, another one is the fluctuating motion or component. Mean motion is characterized by u bar, and the fluctuating component, this is my fluctuating component u prime. So u prime, that is velocity at any instant u is equal to u bar plus u prime. So it is not that u prime is always positive, it can be negative also. It is just that I have given that as u equal to u bar plus u prime. Now let us say this is some time t naught and let us say some other time t naught plus t. Now before I do this definition of u bar and u prime, we should understand how can I measure this. Can I measure this with pitot tube? See, let us say we all know that we have a pipe. Now if I insert a pitot tube, this measures total pressure. Now if I have a static tap here, it will measure static pressure. So you get P total is equal to P static plus half rho u, let us say this u center line square. So that means you get the, at this location you get the velocity. If you connect this to manometer, you are going to get UCL bar, because it cannot, manometer is a very slow device, I mean it is having a lot of inertia, it cannot respond fast. So you will be able to measure only the mean motion. But on the other hand, if you use, let us say, hot wire anemometer. What is hot wire anemometer? Hot wire anemometer is a small wire which is held between two prongs, And how small is this diameter? Diameter of the wire is 15 micrometer. To just give the feel what does 15 micrometer means, our hair diameter is roughly 75 micrometer. So the hot wire anemometer is 5 times lower than the diameter of the hair. That means so small it is. In fact, you will have to keep this to the tube light to get this, to see it. With the bare eye it is very difficult to see this. So that it has less, it is made of platinum rhodium and along with little bit of stainless steel. So this wire is made as a part of a Wheatstone bridge. It is made as one arm of the Wheatstone bridge. That is, this is my hot wire anemometer and this is my voltage what I am supplying, okay, the battery voltage. Now this is the output what I get as the output voltage. Now it is initially maintained at 400 degrees Celsius, let us say. It is maintained at a constant temperature. This is what is called a CTA, constant temperature anemometer. So maintained at 400 degrees Celsius, so you have supplied some supply voltage. Now you put this wire in the flow, what happens? The wire gets cooled. You have to bring back this wire to the same temperature 400 degrees Celsius. To do that you supply some additional voltage. So there is a change in the voltage output because of the change in the supply. So you get E squared equal to E naught squared plus Bu to the power of n, where E is the voltage after you have introduced in the flow, in flow. E naught is voltage without flow, and B and N are constants which come from calibration, and U is the velocity. This is what is called King's law. Using this one can get both U bar and U prime. If you differentiate this equation you can get U prime also. So the point is you can get the mean motion generally with the pitot tube and the fluctuating component with the hot wire anemometer. So but then now let us try to define this U bar. What is U bar? U bar is 1 by T integral of T naught to T naught plus T U dt. Of course U is a function of x, y and z, but I have taken one location. Now what is U? I have just put U bar plus U prime. So you get 1 by T equal to, that is this is the definition of U bar. Let us keep it like that. Now U equal to U bar plus U prime. Now what is U prime? U prime equal to U minus U bar. Now let me ask, what would be the value of U prime bar? Again by this definition, 1 by T integral within the limits T naught to T naught plus T U prime dt. Now U prime, I have just now found U minus U bar. Let me just substitute that. 1 by T integral of T naught to T naught plus T U minus U bar dt. So if I just take out 1 by T integral of U dt T naught to T naught plus T minus of 1 by T integral of T naught to T naught plus T U bar dt, U bar dt. So now what will I get? So U prime bar equal to, this is nothing but by definition the same as U bar. So U bar minus of, if I integrate this, U bar can be taken out. So U bar into T, that is you get directly T by T. Okay. So I am not substituting and all doing that. So you get essentially 0 because T gets cancelled out. So then you have U bar getting cancelled out, so you end up getting 0. So u prime bar, what is that you get? U prime bar is 0. So then how do I quantify this fluctuating component? See, we know how to quantify now the mean component. How do I quantify this fluctuating component? This has happened, u prime bar has happened 0 because if you just see here, you don't have to do maths also. If you just see here, there are pluses, minuses, pluses, minuses. If you integrate for a long time, pluses, minuses just get cancelled out. So u prime is not going to help because there are minuses. To make that minus as plus, the only way to do is u prime square. Let me square it. If I square that, that is u prime square bar. U prime square bar would be 1 by t integral of t naught to t naught plus t u prime squared dt. So this is not going to get 0. This is not going to get 0. This is defined. We define what is called turbulence intensity, Ti, is equal to u prime squared bar. I square root it. Why? Because u prime squared bar is having unit of meter squared per second squared, but instead of that I want meters per second. I divide it by u bar into 100. So this is the typical definition of turbulence intensity. In most of the times, if you are doing fluent or something, you will have to give this Ti as the input along with the mean flow. So this is that turbulence intensity. Now how long I should take this T? If I ask this question, how long I should take this, how long I should average? When you are doing experiments, depending on the class of the flow, whether it is a internal flow, external flow or jet flow, typically you can say that typically you will average for 1 minute, or you would decide that 1 minute like this. You would first average it for 1 minute, next you will average for 2 minutes, next 3 minutes or half a minute, until your u bar doesn't vary with your duration over which you have integrated. So T, one thing I should say that T should be sufficiently long so that u bar is independent of T. That's the criterion for choosing T. Now there are few rules because we need to take up, the next step is to take up the mass, momentum and energy equation and then average it. So there are few rules which I want to state. We will apply those rules. F double bar, if you are time averaging twice, it's equal to F bar. I am not proving this, without proof I am stating. F plus G bar is equal to F bar plus G bar. You can prove it from definition, it's not very difficult. F bar dot G bar equal to F bar dot G bar. Then next important, del F by del S bar is equal to del F bar by del S. Integral of F dot ds bar is equal to integral of F bar dot ds. These are few rules which I am going to use everywhere in my relations. So if you just take, just for a practice, if you just take u squared, u is nothing but u prime plus u bar whole squared. Now this is going to be u prime squared plus 2u prime u bar plus u bar squared. If you time average this u squared bar, so what will you get? You will get u prime squared bar plus, let me take this term first, u bar squared plus 2u bar is common, you will take out, but if you time average u prime, that is, you can write this as u bar u prime, but what will happen to this u bar u prime? U bar u prime bar will be equal to 1 by t integral of u bar u prime t 0 to, let's say, t naught to t naught plus t. Now u bar is independent of t, so you can take out u bar by t, and we have already found that integral of u prime is going to fetch us 0. So this is going to give me 0. So you will end up getting only u prime squared bar plus u bar squared. Okay. So next is, you have uv bar is equal to, similarly if you just do, you will get u bar v bar plus u prime v prime bar plus u prime v bar bar plus u bar v prime bar, but this and this will get cancelled out, so you are ending up with only this. Okay. Now let us take up the Reynolds averaging of the equations, but I will consider 3D incompressible flow. 3D incompressible flow. Okay. So let me just write continuity equation, that is del u by del x plus del v by del y plus del w by del z is equal to 0. Rho del u by del t plus u del u by del x plus v del u by del y plus w del u by del z is equal to minus del p by del x plus mu del squared u by del x squared plus del squared u by del y squared plus del squared u by del z squared. You can write like this for y and z momentum equation. So if I write temperature, before we write the temperature, so let us just try to Reynolds average the continuity equation, that is del u by del x plus del v by del y plus del w by del z equal to 0. So I can replace u with u bar plus u prime, v with v bar plus v prime, and w with w bar plus w prime. So you get u bar plus u prime upon del x plus del v bar plus v prime by del y plus del w bar plus w prime by del z. Now we are time averaging. So if we are time averaging, this is equal to 0. So now you get del u bar plus u prime bar upon del x plus, because we are using one of the formulae, v bar plus v prime bar by del y plus del of w bar plus w prime bar by del z is equal to 0. So now if I just take del u bar plus u prime bar by del x term, so I can write this as del u bar by del x plus del u prime bar by del x. As we know, u prime bar is 0. So this term vanishes. So I get this as del u bar by del x. So whole of this continuity equation reduces to del u bar by del x plus del v bar by del y plus del w bar by del z equal to 0. So in the next module, we shall take up the momentum equation and Reynolds average the momentum equation in the next module. Thank you.